Hello, welcome back to Physics 211. We have been talking about moving charges. We have moved on to moving charges, and we've seen that moving charges or currents are when charges can move. And now we're going to look at a couple important concepts, including the fact that those currents are actually conserved. So we can have conservation of charge, which leads to conservation of current. And then the fact that we have conservation of current will help us understand another one of Kirchoff's laws. Then we will look at how there's a relationship between the potential difference and the current, and how we can see that there is a direct relationship between the current and whatever that voltage, that potential difference is that we have across it. So let's get started by looking at this idea of conservation of current. So this figure shows two light bulbs inside our wire that is connecting our charged capacitor plates. So we had our charged capacitor plates and we connected them with a wire to discharge them. And so we know that when we connected the plates with the wire, they were now discharging. But now that we have these light bulbs here, light bulb A, light bulb B, that are in the circuit of our wire, we can see that those will actually light up as the capacitor discharges. So as the capacitor discharges, the current through both bulbs is lighting them up, and they're lighting up the same amount, which tells us that the current is exactly the same through both bulbs. It's not brighter. Light bulb B is not brighter than light bulb A. Light bulb A is not brighter than light bulb B. They are the same. So the current going through each bulb is the same. So what we know is that this tells us that due to conservation of current, the rate of the electrons leaving a light bulb, or if we had some other device in there, just easy to see with a light bulb, is exactly the same as the rate of the electrons entering the light bulb. So now that we can see this using light bulbs, let's look and see what's going on inside our wire. So let's go inside our wire and look at what's going on there on a micro scale. So inside the wire, we can say that due to conservation of charge, the current must be the same at all points in a current carrying wire. So the point here is equal to the point here. The current in the wire is the same at all points. So the current is constant through our wire. Well, that's great for a single wire, but this can be very helpful when we get into a circuit. So let's look now at what happens if we have a wire that then breaks into two different pieces. So we have a wire here, and then we have a junction, and we have two different wires coming out in this direction. And we see that this is our input current, and these are output currents. And due to conservation of charge, what we have here is that at a junction, the law of conservation of current requires that the current going in, the sum of all the currents going in, must equal the sum of all the currents going out. So this current coming in is equal to the sum of these two currents going out. The sum of the currents going in equals the sum of the currents going out. This basic conservation statement is called Kirchoff's junction law. So we end up with Kirchoff's junction law, just like Kirchoff's other law that we already saw, which was Kirchoff's loop law that told us that when we go all the way around a loop, the change in the potential will end up coming back to zero if we go all the way around a loop. All right, now we want to start talking about a couple other important ideas. And those are the ideas of conductivity and resistivity. In order to understand the ideas of conductivity and resistivity, I want to go back a little bit and talk about the electron current. So remember that our electron current is the electrons that are going over in a certain amount of time. So it's a number of electrons per time that is passing in a certain point. And so that we saw that was directly proportional to the electric field strength, E. So here is the electron current is directly proportional to electric field strength E, because right here we have N sub E is the electron density, and tau is our mean time between collisions, that's tau, and those are just properties of the metal. And then little e, of course, is just the charge of the electron. M is the mass of the electron. And A is the area of the cross-sectional area of our conducting surface, of our wire usually. And so all of these right here, this is just a constant. This constant times the electric field. So that tells us that the electron current is directly proportional to the electric field strength. Now, that's the electron current. And we know the electron current is related to the current that we usually talk about, which is the current of, which indicates the direction that positive charges should flow. Thanks, Benjamin Franklin. So this is the current that we usually talk about, that's capital I, and that's related to our electron current as the charge of the electron, little e, times I sub e, the electron current. So I can take this expression here that we have for the electron current and put it in down here, and I see that the current itself is going to be equal to the electron density times, now I have two e's, so it'll be e squared times tau times the area, cross-sectional area, over the mass of the electron times the electric field. So that's how we can then see that the current is also directly proportional to the electric field strength. Now we've also defined the current density, and we saw that the current density J is equal to the current over the area. So if I take my expression here for my current and I put it in here, I can see that my current density is equal to my electron density times the charge of my electron squared times tau times the area over the mass of my electron times the area times the electric field strength. And so my areas will cancel, and I see that the current density is then equal to the electron density times the charge of the electron squared times the mean time between collisions tau over the mass of the electron times the electric field strength. And this expression, this part right here, this is a constant. And this constant is due just to the properties of the metal. It's got the electron density, and it's got the time between collisions tau, and then of course it just has the charge of the electron squared over the mass of the electron. And so we can use this constant right here, and we define it. We define it as our conductivity. So this is the conductivity of a material, and it is defined as the electron density times the charge of the electron squared times the mean time between collisions tau over the mass of the electron. And this, again, is conductivity. And like density, it just characterizes a material as a whole. So this is the same for any type of that material. So if we know what it is for aluminum, it's that type. It's always going to be that for aluminum, for example. Now, the current density, J, is going to be related to the electric field, because we said it was that J would be equal to this constant times the electric field. So we can then write it instead as J equals sigma, where sigma is the conductivity times E. So that's the conductivity. And a material with greater conductivity will have a greater charge, it will have a greater current density if we have for the electric field that is applied to it. So if we apply an electric field, it'll have a greater current density. So that will be the current per area. And that's the conductivity. Now we can also create another we can also talk about another property of a metal by just saying another property of a material by looking at the inverse of the conductivity. So we might want to know how conductive it is, but we might want to also know its resistivity. So that tells us how reluctantly the electrons move in response to an electric field. So this is the resistivity, and it is just the inverse of the conductivity. It's how reluctantly the electrons move in response to an electric field. And so it is the inverse of the conductivity. We use the letter rho for the resistivity. I know we've used it for other things as well. That's 1 over sigma, sigma being the conductivity. And so if I take this expression for my conductivity and put it here, I'll now have 1 over this will be my resistivity. So that'll be the mass of my electron over the electron density times the charge of the electron squared times tau. So this is just a property, both the conductivity and the resistivity, which is just the inverse of the conductivity and vice versa. Those are just properties of our materials. So we can look at the resistivity and conductivity of different conducting materials. So for aluminum, for example, we have the resistivity, it's 2.8 times 10 to the minus 8th. That's ohms, meters are the units for resistivity. And so the inverse of that is the conductivity. And so that's going to be 3.5 times 10 to the 7th. And that is ohms to the minus 1, meters to the minus 1, because that's the inverse. And we can look at that for different metals, and we see that the resistivity, again, is the inverse of the conductivity, and it is specific to the material. Now, this idea of resistivity is useful, and now we're going to look at how we can use resistivity to help us see how that relates to the current through a particular wire. So we're going to look at not just the resistivity, but something called the resistance. And to get there, we're going to start by looking at this figure that shows a section of a conductor in which an electric field E is creating current I by pushing charge carriers in the opposite direction, but that's okay. So we have our current I, which goes in the same direction as our electric field, because that's the direction positive charges would move. But in fact, we know that the electrons are moving in the opposite direction. And so they're moving along by this electric field. Now, we know that from before that our electric field strength, well, the electric field is equal to negative the difference in the potential over the distance that it's traveled. So we're looking in a certain direction. So it's going in this direction here. We'll call this our S here. So if this is S in this direction, then it would be negative delta V over delta S. And of course, we remember that in the limit as delta S goes to 0, that gave us E sub S equals negative dV ds. So we've got, we're not going to take the limit as delta S goes to 0 because our delta S is just this length of the wire right here. So this is the length of our wire. That's our delta S. And so if that's our delta S, we see that in this case, here's the length of our wire is our delta S. Here is our potential difference that's creating our electric field inside the conductor, and that's causing the charges to flow through it. So here is our delta V. And our delta S is just this L right here. That's our delta S in this case. And so, and these lines right here, of course, are our equipotential surfaces that are perpendicular to our electric field. And so if we use this expression here for the electric field, and we just want the magnitude of it. So I'm not gonna worry about the negative side, I just want the magnitude of it. We know that our electric field, the magnitude of it, that's all I'm worried about, is equal to our delta V over delta S. And so over here, the strength of the field is just going to be E equals delta V over delta S, where delta S in this case is just this length, the total length here. This is our delta S right here, this length of our wire. And so we can rewrite that as delta V over L, the length of our wire. So now I want to relate this to the current. And to relate this to the current, I'm going to start by relating it, as we had done just a second ago, to the current density. And so we saw that the current density, remember, is J equals the current over the area, I over A. And we saw that that was equal to the conductivity sigma times the electric field. Now, sigma, we remember, is the same as 1 over the resistivity. I'm trying to get a relationship between the current and the resistivity. And so in that case, in the electric field, and so in that case, I want to see that the current here over A is going to be equal to the electric field over rho. And so I can rewrite that as the current and multiply both sides by A is going to be equal to A over my resistivity times the strength of my electric field. Now I know that the strength of my electric field is the change in the potential over L. And so I can rewrite this, and I can see that the current is then going to be related to delta V by I equals A over rho times L delta V. So I put the delta V over L in here, and I see that now the current is equal to the area over the resistivity times the length times the change in the potential. So the current is directly related to the change in the potential because this is all a constant that is dependent on the area of our wire and the length of our wire and the material that it's made of. That resistivity is based on its material. And this right here is what we call our resistance. And we see that the current is directly related to the potential difference. So the current through a conductor is proportional to the potential difference between its ends. And now we're going to define the resistance R of a long thin wire, of a long thin conductor of length L and cross-sectional area A. So this is going to be our resistance R. And we just saw what that was. That's going to be R equals the resistivity rho times the length over A. And the units of resistance is the ohm, where 1 ohm is equal to 1 volt per ampere. And we can see that because the current through a conductor is going to be determined by the potential difference delta V along its length. So I equals delta V over R. And so this is called Ohm's law. And as I've said before, we can rewrite this. I like to write this as delta V equals I times R. And I remember that when we're cold, we say ver, ver. That's how we remember Ohm's law. It's a ver. And that is Ohm's law, where we see that the current is directly related to the difference in the potential, and it's directly related to the difference in the potential as 1 over the resistance.